Hello, everybody. Thanks for coming. I'm Fengshi Niu, and today I'm going to talk about auction throttling and causal inference of online advertising effects. This is a joint project with George Gui and Harikesh Nair. The motivation for this project is the following. Measuring the effect of advertising is important for advertisers and publishers. Advertisers are interested in evaluating and optimize advertising campaigns, and publishers are interested in optimizing auction designs and ad inventory. One problem is that experimentation can be expensive. Typically, we require large-scale experiment to have enough statistical power, which may hurt user experience and advertising profit. It is therefore valuable to identify pervasive quasi-experimental variation already in the data, and this will be the focus of this talk. The project is identify probability throttling as which is an ad campaign budget control mechanism as a source of quasi-experiment variation. And this kind of budget control mechanism is already used by many ad publishers or platforms, including Google, Facebook, and JD.com. We will demonstrate that ad auction participation under throttling is conditionally random, and because it is part of the existing ad serving logic, there's no extra cost of leveraging this data other than implementing an estimator on top of it, and we will do this. We will focus on the average treatment effect on the treated as the main target. This is an incredibly valuable estimate for advertisers who are interested in evaluating the campaign effectiveness. All right, so let's talk about budget control mechanisms. And to give you some context, let's consider three entities here. Advertisers, customers, and platform or publishers. Advertisers are interested in sending ads to eligible customers by bidding and winning ad auctions. They often ask the publisher to facilitate a campaign for them. And the platform and publisher will participate by bidding in those auctions on behalf of the advertiser, and usually the advertiser also have a budget constraint, and the platform and publisher needs to make sure that the advertiser does not overspend or does not exhaust their budget too early by implementing some form of budget control mechanisms. And so here comes an example of what the auction participation looked like without any budget control. Early on in the campaign, the participation, as you can see, is 100%. Whenever there's an auction, the advertiser will join the auction by participating. And later on, the advertiser can no longer participate in any of the remaining campaign because the budget has already been exhausted, even though there's still 40% of campaign time left. So now there are two major ways of implementing the budget control. The first way is called bid shading. And bid shading means adjusting bids based on the spending rate. When, for example, the remaining budget is low, they're going to reduce the bid. And one problem with bid shading is it is not transparent, in the sense that even if the advertiser sets a bid to a prefix value, the bid will still be adjusted by the platform according to their heuristic rules. And the second way is called probability throttling. And so here, what will happen is the auction participation is adjusted based on spending rate. And advertisers are randomly thrown out of an auction if the remaining budget is low. This is implemented by platforms including Google, Facebook, and JD.com, among others, so it is very common. And the key observation here is under probability throttling. There's clean and free random variation in the data, and we will use this variation to measure the ad effects. To show you how the throttling procedure actually works, consider the following scenario. So customer I is visiting the platform. The platform will calculate the auction participation probability for the focal advertiser based on its ad spending rate and remaining budget. And based on this calculation, so we get this participation probability, which is denoted as P here. The advertiser will be randomly selected into participating in the auction with probability P. And with probability 1 minus P, the advertiser is not going to participate in this auction. And this probability P here is the key output of the auction throttling algorithm. Here's an example of what the auction participation may look like under throttling. So early on, participation, as we can see here, is high, but not 100% because the platform still think there's a chance that the advertiser may run out of the budget later on. And later, the participation is low. As you can see, most of them are 0. But not exact. The probability is not exactly 0, because for some of the auctions, they still participate. And the key here is to recognize that there exists variation in auction participations throughout the course of the campaign under this throttling algorithm. Okay, and now that we understand what the probability throttling is doing, I want to discuss how exactly we're going to use random variation from auction throttling to identify the treatment effect of ad exposure. And the key here is conditional on the participation probability P. Auction participation Z is actually conditionally exogenous. So auction participation given P is exactly just the same as flipping a biased coin with probability P. So it's exogenous with respect to anything else. And this together with the fact that auction participation affects the ad exposure, which is called relevance, and auction participation affects purchase only by affecting ad exposure, which is called exclusion, implies that auction participation is a valid conditional instrumental variable for estimating the effect of ad exposure on purchase, conditionally given the participation probability P. So for those of you who are familiar with instrumental variable approach, essentially if we are conditioning on the participation probability, or we are having an encouragement design in which the auction participation, the instrumental variable here, is randomly assigned. Okay, great. So now we're ready to talk about the estimation method we're going to use. Remember that the objective here is to estimate so-called average treatment effect on the treated, which is defined as, which is denoted as tau and defined as the conditional expectation of the treatment effect given the realized treatment is actually equal to 1. Here in this mathematical expression, we're using y0 and y1 to denote the potential purchase decision for individual I under no ad exposure and under ad exposure. And D here is the ad exposure is a binary indicator, and Z is auction participation, which is a conditional instrumental variable we're going to use. And the P is the participation probability, which is what we're going to condition now. And we have some assumptions. First, the participation probability is non-degenerate, so it's strictly between 0 and 1. And also, there's an additional assumption which is kind of substantial, saying that we are assuming each individual is exposed to one and only one auction, and this is called a single exposure assumption. And so here comes our estimator. The population we have consists of all auctions targeted by the campaign, okay? And for different auctions, they're going to have different corresponding participation probability. And we're going to partition this population based on the participation probability. So within each subpopulation, the units are having exactly the same participation probability. And this is the way we achieve conditioning on participation probability. And then within each partition, within each subgroup, we're going to have a corresponding estimate for the average treatment effect on the treated. And then in the last stage, we're going to take a weighted average of this subgroup level average treatment effect on a treated estimate to arrive at an overall ATT estimate. So here's how we estimate average treatment effect on a treated for each subpopulation. Remember, in our case, we have one-sided compliance in the sense that if the participation is zero, the ad exposure is always zero. Well, only when the participation is one, there's a chance that the ad exposure is one. And under this scenario, we know that the ATT coincides with the local average treatment effect defined by the ratio of intent to treat effect on the outcome divided by the intent to treat effect on the treatment. And based on this fact, what we know is we can use the classic instrumental variable estimator to get an estimate of this ATT, namely we can use two-stage least-square estimator. And the only thing left is assigning weights for each of the subgroup and take the weighted average. And we are going to calculate the weight according to the number of treated units in the subgroup divided by the number of treated units over the whole population, so that we are actually estimating the ATT over the whole population. Okay, and to summarize, our estimation procedure has three parts. In the first step is split the overall population based on participation probability. Within each subgroup, we estimate ATT by the classic instrumental variable estimate. And in the third step, we combine them by weighting according to the number of treated units in that subgroup. Okay, here comes our simulation. We have a very simple simulation setup in which there are two kinds of users. The high type has larger treatment effects and higher competing bids than the low type users and low type customers. And the simulation, in a simulation, the throttling mechanism is designed in a way so that when there's a higher recent expenditure rate, we assign low participation probability to the campaign. And here's a big picture result. Our method has low bias and low mean square error compared to the kind of naive method that one may want to use with, for example, running a regression of the outcome variable on the treatment variable, let's call it OS, or running an unconditional instrumental variable instead of a conditional instrumental variable and weighted average approach like ours. Okay, so our method outperformed those naive baselines in simulation. And for real data, we actually run our method on data collected from JD.com. So in this data set, there are campaigns data from 9 different hours, and it's 1 hour per day at 11 p.m. for 9 days. And the overall population has 1.5 million auctions amid the campaign's targeting criteria. So it's a pretty large sample size. And as we can see, the participation probability is somewhere between 0.3 to 0.75 and across the 9 different subgroups. And here's the average treatment effect on the traded within each subgroup. And we see that out of 9 total subgroups, 8 of them has positive and statistically significant effect at 90% confidence, which is promising. And in terms of overall average treatment effect on the traded, our method says the point estimate is about 3.5%, and it has a small standard error, and the effect is statistically significant at 99% confidence. And so here comes the conclusion. In our project, we identify auction throttling as a source of pervasive and naturally occurring variation on ad platforms. And we outlined a way to leverage this variation to measure the causal effects of digital ad campaigns sold via auctions. And the idea is, in this sort of setting, auction participation is a conditional instrumental variable under probability throttling given the participation probability. And we developed an estimation and weighting procedure to estimate the average trading effect on traded. And we illustrated our method on data from JD.com. And in this particular data set, we see that the variation is pervasive to allow our method to estimate things precisely at the hourly level. And our method generates insightful and precise estimate of ad effects with almost no cost. Thank you very much.